All right, friends, welcome back. Hope you had a good weekend. When we were here on Friday, at the very end, we were talking about the issue of kinetics, which is how reactions happen. Thermodynamics tells you why they happen, and that's generally because the bonds that you form are more stable than the bonds that you broke. But kinetics will tell you in what order things happen, which happens first, which bond breaks first, which bond forms first, in what order, and how fast does it go. And mechanism is really important in organic chemistry because if you understand it, you can predict outcomes of reactions in different circumstances, and you can also propose ways to make reactions better. So we were dealing with this substitution reaction. It is called a substitution reaction because the nucleophile highlighted in purple, here Cn-, is replacing what I've called the leaving group highlighted in green. The leaving group is I-, but before on the electrophile it was a carbon iodide bond. And we break the carbon iodide bond, we make the carbon-carbon bond. If you looked at bond strengths or energies, you would conclude that the reaction should be downhill in energy for a couple of reasons. First, just looking at the strength of the carbon iodide sigma bond versus the carbon-carbon sigma bond, the carbon-carbon sigma bond is stronger. The second thing that would help you know this is downhill in energy is that Cn- is less stable than I-. And you could get that just by comparing the pKa's of their conjugate acids. If you looked at a pKa table, the pKa of HI is like minus 13 or minus 11. The pKa of HCN is like 9. So I- is much more stable of a conjugate base than is Cn-. Anyway, that's thermodynamics, but in what order do these things happen is what we were dealing with. And our first hypothesis was maybe it's stepwise. Maybe we break the carbon iodide bond first, we get an intermediate, and then maybe we make the carbon-carbon bond. So we talked about what that first step would be, and it would be essentially the leaving group leaves, which I'm showing with an arrow starting with the carbon iodide bond and pointing to the iodide to indicate that iodide leaves with the electrons in that carbon iodide bond. And you get to this intermediate, which I'll draw a little bit in more detail. I'm getting texts from political campaigns right now. Somebody wants me to vote for a particular candidate in the Vineyard mayor race. Yay. Okay. Anyway, this is the intermediate. It is a carbocation. And we said we expected this to be uphill in energy. Why? Why should it be uphill? Because you're breaking bonds, and bond breaking is always unfavorable, right? Okay, good. Now, we talked about what the transition state for the reaction would look like. A transition state is an energy maximum between two energy minima. In this case, the energy minima are a starting material and an intermediate. Transition state is the energy maximum between those two, and it's going to look like this. Basically, the carbon iodide bond is going to be getting longer and weaker. And in the transition state, you expect there to be a buildup of partial positive charge on the carbon and a buildup of partial negative charge on the iodide. All right, that's the transition state for reaction 1. In the second step, we propose that the nucleophile, Cn-, attacks the carbocation to give you the product, which has the new carbon iodide bond. And we expect the transition state for that reaction to look somewhat similar to the transition state for the first reaction, in the sense that we expect the carbon bond to be partially forming, with partial positive on the carbon and partial negative on the CN minus. This notation with the bracket and the double dagger indicates that this is a transition state. If we were to draw an energy diagram for this reaction, on the y-axis would be energy. On the x-axis would be something that we're just going to call reaction progress. You can make that quantitative by defining things that change in the reaction, and basically you go from 0% done to 100% done for the reaction. We won't worry about that. We're going to just keep it pretty generic as just reaction progress. Starting material we're going to put here. Products, we said, are more stable than the starting materials. And then we said that the intermediate, because the reaction's uphill, we said that the intermediate should be higher in energy than the starting material. That intermediate is the carbocation. So let's put that here. And you expect to go through a high energy transition state. That's transition state 1. That looks like what we've drawn here, to get to the energy minimum that is the intermediate. And then from that intermediate, you go over a second transition state to get to the products. You expect the second transition state to be lower in energy than the first transition state, because in the first transition state, you're breaking a bond. In the second one, you're starting to make a bond. In any case, the energy difference between the starting material and the first transition state is called the activation energy for that first step. And you can see that the activation energy for the first step is much smaller, or much larger rather, than the activation energy for the second step. The delta G with the double dagger is activation energy. You may have called that E with a subscript A in general chemistry. And so the step with the largest activation energy is what we're going to call the rate determining step. It's going to be the one that determines the rate of the reaction. I think that's mostly reviewed. Did you talk about that in Gen Chem? Pretty much? Okay. Somebody always wants to know at this stage, what if there was a reaction where the first transition state had a really big activation energy, but the second transition state was even higher in energy? What would the kinetics be like there? There are people that look into that, but we're not going to be dealing with anything that complicated in organic chemistry at this level. All right, so because in this mechanism, the activation energy for the first step is so much greater than the activation energy for the second step, the rate depends on the first step only. So if we were to write a rate law for this reaction, where we would show how the rate depends on the concentrations of the starting material, we would expect that rate law to only involve things in the first step. So the rate law is going to have a constant K. That is the rate constant. We always use the letter K for rate constant. I'm not sure, other than rate constant, maybe, is K. In any case, it is related to activation energy for the rate determining step. So if that activation energy gets smaller, then rate constant gets bigger. And this goes with your intuition. The reaction rate should increase if you don't have to go up quite as large of a hill. The second portion of the rate law is just the concentration of the things that are in the rate determining step. And for this mechanism that we're proposing, it's only methyl iodide because Cn minus isn't involved in the rate determining step. So we would say that this rate law is first order in methyl iodide, meaning first order or linear in methyl iodide. First order means the concentration term in the rate law has an exponent of 1, or that only one molecule of methyl iodide is involved in the rate determining step. Okay? We would say that it is 0 order in Cn minus because Cn minus doesn't appear in the rate law. Alternatively, you could say that it was there, but that the exponent on it was 0, and any number raised to the 0 is 1. So, okay. Questions about that? So we can start to make some predictions about this mechanism that would allow us to do experiments to determine whether this mechanism was actually what was operating. One of the easiest things to do is to measure the rate of the reaction as a function of concentration of the starting materials. Based on this rate law, if I change the concentration of methyl iodide, what do I predict happens to the rate of the reaction? If I increase methyl iodide concentration, what should happen to the rate of the reaction? It should also increase, and the rate law says it should do so linearly. All right? So if I did this experiment where I increase the concentration of methyl iodide linearly, I should see the rate increase linearly. All right. Now, what about if this mechanism is real, if this mechanism is how the reaction's working? What does the rate law tell me should happen if I increase the concentration of Cn minus? Nothing happens. It stays the same because the rate doesn't depend on the concentration of Cn minus. Okay? So this would be evidence that our rate law is accurate and that the reaction proceeds through this mechanism. Somebody always wants to know at this stage, how is this even possible that the reaction doesn't depend on the rate of Cn minus? If this were the mechanism and I had no Cn minus present, the reaction couldn't happen, right? And I say, you're absolutely right, and at really, really low concentrations of Cn minus, the rate law changes in ways that you don't want to know about, but if you do, come take Chemistry 552 from me or my colleague Dan S., and we would be happy to explain it to you in greater detail, all right? So many years teaching, no takers on that one. Just nobody wants to do that. It's fine. Okay. This mechanistic hypothesis has a name. This is a mechanism for a substitution reaction. It involves a nucleophile replacing the leaving group, and the rate law only has one concentration term in it, so we're going to call that unimolecular, meaning first order overall, only one concentration term. And the abbreviation for that is going to be SN1. That's the abbreviation for this mechanistic hypothesis where the leaving group leaves first, you get a carbocationic intermediate, and then you get the product because the nucleophile attacks. There's one other interesting piece of evidence that can support an SN1 mechanism. And to see this, we need to change our starting material a little bit. So if the mechanism was SN1, let's start with a chiral starting material. Let's have the leaving group be Br. And let's just have the nucleophile be some generic negatively charged nucleophile. If the reaction were SN1, And this starting material is chiral, and there is a stereocenter, and there it is. If the reaction mechanism were SN1, you would predict that the leaving group would leave to give you this carbocation, and then in a second step, the nucleophile would attack. Now, tell me, is that carbocation chiral? Not chiral. How can you tell it's not chiral? It doesn't have a stereocenter, and if you drew its mirror image, it's the same thing as its mirror image. Okay? So we have lost chirality, and when you lose chirality, anything that happens from there on has to either generate a not chiral product or a racemic mixture of enantiomers. Let's show you what happens here, and to do this we need to draw on something you learned for exam 1, which is HOMO and LUMO. What is the LUMO of the carbocation? Empty p orbital on the positively charged carbon. And from our perspective, looking down on this planar carbocation, we see a large lobe pointing towards us, and then another lobe going back into the plane of the page. If we put ourselves in the page and looked at this molecule from the side, what would we see? It would look like this. It would be planar, and there would be a large lobe pointing up and another large lobe pointing down. Same size on either side. And it turns out that both faces, the top face and the bottom face of this carbocation, are identical. They appear exactly the same. And that means that a nucleophile has to attack from above at exactly the same rate as it might attack from below. Either of those options has to happen 50% of the time. There can be no preference for top versus bottom when the top face and the bottom face are exactly the same, okay? So that means that 50% of the time, you're gonna get the product of attack from the top, which looks like this. And the other 50% of the time, you're gonna get the product of attack from below, which looks like this. And if you're following along, that would be, if we redrew the molecule, that would look like this or like this. We get a racemate, or a 1-to-1 mixture of enantiomers. Okay, so the stereochemical outcome of an SN1 reaction is that we lose the 100% pure enantiomer in the starting material, and we get a racemate. We get a 1-to-1 mixture of enantiomers in the product. And it's because of that positively charged intermediate where you can attack the p orbital from either side. Yeah? That's right. So the product that I haven't showed here is the leaving group that left. Yep. Good. Others? Yes?
So that nucleophile that's attached to 50% in top and bottom face, is it like one electron and happy molecule?
No, what we mean in 50%, we don't mean one nucleophile attacks from above or below. We mean it's one molecule's got to make a choice. So one of them will attack from above, one of them will, in another case, will attack from below. On average, though, you have to get half and half. Yep. Okay, others? Okay, so we're learning that you can do rate experiments and you can use stereochemistry as an indicator of reaction mechanism. Let's now consider an alternative mechanistic hypothesis. And that is a mechanism where we break the carbon iodide sigma bond and make the carbon-carbon sigma bond in the same step or at the same time. Incidentally, why am I not proposing a third mechanistic hypothesis where we would make the carbon-carbon bond first and then the carbon iodide bond would break? What would be the problem with that? Go ahead.
We can't have Texas carbon.
No Texas carbons. We love the great state of Texas. It is large, but it is not so large that carbon can make 5 bonds in the great state of Texas. Yep. So you break the octet rule if the carbon has 5 bonds to it. Okay, good. So second mechanistic hypothesis is we're going to break the CI bond at the same time as we're making the CC bond. So that would look something like this. Here's Cn minus, and then in a single step, you propose to replace Cn minus with, or replace I minus with Cn minus. Okay. Now, I'm hedging a little bit as we're drawing this because we could consider multiple possible transition states. One transition state for this reaction might look like this. You have the carbon iodide bond weakening and getting longer. At the same time, you have the carbon-carbon bond getting stronger and shorter. And one hypothesis is that the nucleophile, Cn minus, comes in from the same side that the I minus is leaving from. So that's one possible transition state. Another possible transition state would look like this. Iodide is going to be leaving from one side at the same time as Cn minus is coming in from the other side. And in order for this to happen, it's almost as though the carbon that before was sp3 hybridized has sort of flattened out to become sp2 hybridized. So this is a transition state that where the nucleophile comes in from the backside attack. Now, we want to resolve this issue pretty early because you're going to see it has some stereochemical consequences. So what do you think? If you had to pick, which of these do you think is better or more favorable, and why? Yeah, go ahead.
The backside, because you have 2 negative charges on the opposite end of each other.
Okay, right. So backside attack minimizes, you're expecting it to minimize electron repulsion. I'm running out of space for repulsion between the leaving group that's leaving and the nucleophile that's coming in. Okay, good. Other reasons. Yeah, go ahead.
I think if I utilize electron repulsion, it could off the leaving group.
Okay, so maybe we're using electron repulsion to kick off the leaving group, or does that mean you're in favor of this one?
The one on the right.
The one on the right, okay. Right, if it comes in from the backside, maybe that electron repulsion is part of what kicks off the leaving group in the first place. Good. Others? Somebody's Sometimes I can't tell regular gestures from hand raising, so this isn't an auction. I don't know, if you want to just like thumb your nose and, yes, go ahead. No, you were just kidding.
No.
You were just itching your nose, okay. All right. What is the LUMO of this molecule? Right, the carbon iodide sigma star. And if we draw that, we have a node in between the two nuclei, smaller lobes pointing towards the node, larger lobes pointing away from the node. So, and we've already discussed why a nucleophile would attack carbon as opposed to iodide, even though the LUMO is both on carbon and iodide. Recall that there are a couple of reasons for that. The first is that there's a small, really small electronegativity difference between carbon and iodide, so carbon's slightly electron poor. But the bigger point is that if the nucleophile attacks carbon, the thing that leaves is I-, which is the conjugate base of a really strong acid. In contrast, if the nucleophile were to attack iodide, the thing that left would be CH3-, which is the conjugate base of an exceedingly weak acid. So we're going to attack the carbon that gives us the better leaving. We're going to attack at the atom that gives us the better leaving group. With that in mind, you can see that if you're going to attack the sigma star on carbon, the only place that is on the backside, 180 degrees away from the carbon iodide bond. So yeah, our second major point is backside attack because that's where the LUMO is. Okay? So we can use these arrows to indicate this one formation of the carbon-carbon bond and this one breaking of the carbon iodide bond in the same step. And yeah, we would conclude that it's backside attack and not same side attack. And in just a minute, you're going to see that backside attack has some stereochemical consequences. But before we do that, let's look at an energy diagram for the process. Let's see, energy is going to be on this axis, and then we're going to have reaction progress on the x-axis. Here's starting material, here's products. We've already said we expect products to be lower in energy than starting materials. There's only one transition state in this reaction because the reaction proceeds in a single step. All of the bond breaking and bond forming happens in the same step. As before, this energy difference here is the activation energy, which determines the rate constant for the reaction. Because there are two molecules involved in the rate determining step, this is the only step of the reaction, so it must be the rate determining step. We expect the rate of this reaction to depend on not only the concentration of the electrophile methyl iodide, but also on the concentration of Cn-. So we would say that this rate law is first order in methyl iodide concentration because the exponent on the methyl iodide concentration is 1. We would say that the reaction is first order in Cn- concentration because Cn- is involved in the rate law and its exponent is 1. But we would say because there are two concentration terms in the rate law, the reaction or the rate law is second order overall, which is another way of saying there are two molecules in the rate determining step. So we'll have an abbreviation for this reaction mechanism proposal. It's related to the abbreviation for the SN1 reaction. This is a substitution reaction. It involves a nucleophile, substitution nucleophilic, but because it involves two molecules in the rate determining step, we're going to call it bimolecular. And that abbreviation will be SN2. So welcome to the next few weeks of your life worrying about SN1 and SN2. Yes?
But
I will tell you that in a moment. Two mechanistic hypotheses. We've learned that the SN1 reaction should be linear rate in methyl iodide concentration, but zero order dependent on Cn minus. Similarly, if the reaction mechanism were SN2, here's how you tell the difference. You change the rate of methyl iodide and you would see the rate go up linearly. If you changed the concentration of Cn minus, you would see the rate go up linearly. And that would be an indication that the SN2 mechanism was preferred. Before the great reveal, we'll cut to commercial and make you wait, or actually, you guys do not know how it used to be when you were watching TV shows and cliffhangers, because today when you see a cliffhanger, you just push next episode and you can watch it. Whereas back when I was a kid and dinosaurs were around, we had to wait for next week, or perhaps even wait through a summer of reruns until the season premiere of the next season. Like, can you even imagine? Anyway, there's an important stereochemical outcome of the SN2 mechanism that you need to be aware of. And you can often use this stereochemical outcome to tell you whether the mechanism was SN2 versus SN1. We're going to, again, go back to that same chiral starting material. If the reaction were SN2 and you use a nucleophile, here's the nucleophile, here's your leaving group. Remember that the outcome of the SN1 reaction was a racemate. Instead, the outcome of the SN2 reaction is what we're going to call 100% stereochemical inversion. Or let's just call it stereochemical inversion. So Y was the bromine used to be a wedge, and now the nucleophile is a dash. And the answer is backside attack. So to illustrate this, we're going to redraw the molecule in a slightly different way. Here is the Br, here is the ethyl group. The methyl group would be pointing out towards us, the hydrogen would be pointing away from us. And I wish I had an animation for this, though if you want to Google animation of an SN2 reaction, you'll be able to find any number of videos that would help with this. The idea is that as the nucleophile approaches from the back side, its electrons repel both the leaving group and the electrons in the carbon-carbon and carbon-hydrogen bonds. And so we'll draw the transition state just to remind you of what it looks like. In the transition state, this has happened to such a degree that the carbon that's being attacked is now no longer sp3 hybridized. It's actually sort of sp2 hybridized as the Br leaves and as the Cn comes in. So this is that transition state. Now you need to imagine what would happen as the Br continues to leave and the Cn continues to come in. As the Br continues to leave, the carbon, hydrogen, and carbon bonds are going to continue to move to the left, or to the right. See, I always get that wrong on the first try. They're to continue to move to the right to avoid the electron repulsion from the incoming nucleophile. And in the end, the nucleophile, oh, I forgot we were just doing a generic nucleophile. Oh well, same thing. All right, afterwards, the nucleophile will replace the leaving group, but is going to be on the completely opposite side of the molecule. as the bromine was. And if you, again, review that molecule and look at it from a slightly different perspective, you have this. Okay? So that's stereochemical inversion. The leaving group used to be a wedge, now the nucleophile is a dash. You might look at that and say, how did the proton, which used to be a dash, become a wedge? And the answer is the nucleophile came in from the backside and pushed the leaving group off and pushed the proton up. An animation of this would help. I wish I had one. I should have done that, but I didn't. Okay, so stereochemical outcome can tell you whether the mechanism was SN1 versus SN2. Notice that you have, in the SN2 case, a pure enantiomer, but you have stereochemical inversion, meaning this used to be a wedge and now it's a dash. Be careful with the meaning of stereochemical inversion. It might not always mean a switch from R to S, because that's going to depend on the priority of the nucleophile versus the leaving group that came in. But stereochemical inversion means it used to be a wedge and now it's a dash, or vice versa. Okay. Yes?
So what happens if the leaving group isn't into the page or out of the page?
What happens if the leaving group isn't into the page or out of the page? You do what I did here, which is you have the nucleophile come in from the opposite side and replace it sort of left to right. Alternatively, you redraw it so that the leaving group is a dash or a wedge. Okay, others? Yeah?
So the reason this one isn't a racemate is because it only attacks from behind?
That's right, because this is not a racemate because it has to be backside attack. It only attacks from behind. Yep.
Follow-up question, why can't it attack from the front side of the field?
Why can't it attack from the front side? And the answer is two things. First, attack from the front side gives you electron-electron repulsion with the leaving group. And second, most of the LUMO's on the back side, so attack from the front side doesn't allow you to attack the LUMO. There is some LUMO here on the front side, but there's a node right there. And so that's not really good orbital overlap.
Okay, so then in what circumstance would we get a racemate?
You get a racemate if the mechanism was SN1.
Okay.
Yep. So stereochemical outcome is a good indicator of whether the mechanism was SN1 versus SN2. Go ahead.
How would you ask us a question?
How would I ask you a question on this? I could, in this case, show you this starting material and these products and say, what did the mechanism have to have been? And you would say SN1. Yeah. When we get better at this, I'm going to give you a starting material and a nucleophile, and I'm going to have you predict the products. And you will need to know, based on the starting material and the nucleophile, whether the mechanism was SN1 or SN2. We're not there yet, but that's where we're going. Yeah?
So what is the best way to be able to determine, like when you're looking at if you go to the bottom where you're talking about the nucleophile and stereochemical inversion, how do you best recognize that when you're just looking at the original product or original starting material?
So if you're asking me how would I have known based on this starting material and the nucleophile that SN2 had to have happened,
Yeah.
I wouldn't. We're not yet ready to predict that. Yeah, but the idea here is if you see stereochemical inversion, that is evidence that the mechanism was SN2. Yeah?
Last class we said a racemate is a lot easier to make than
Yep.
pure chemical. So how much harder is it to influence an SN2 reaction?
So I said last time it's easier to make a racemate than to make a pure enantiomer. So how much harder is the SN2 reaction than the SN1? Not particularly harder. The hard part is getting the starting material. So that's what I meant is if you want to get this pure enantiomer product, you can do it via an SN2 reaction, but you're just kicking the can down the road because now you have to ask, well, where did I get this? Yeah. Okay, did I see another hand somewhere? No? Yeah.
For SN1, where does the energy come from to break the bond over?
Right, so for SN1, that's a great question. Where does the energy come from for the bond to break? And the answer is that bonds vibrate anyway, they wiggle. And so over time, if a molecule gets enough, if a system gets enough kinetic energy, molecules bump into each other and some of their kinetic energy gets transferred to some of the vibrational motion. And if that gets big enough, the iodide can just pop off and go flying off into wherever. You might expect that that's slow, and it is, because you've got to wait for that thing to happen. Okay, others? So let's do the big reveal. Let me tell you what the mechanism is. In this case, stereochemistry doesn't help you because the starting material is not chiral. So there's no way to tell whether you had stereochemical inversion or not. However, you could do the kinetic rate experiments, and if you did, you would conclude that the reaction mechanism here was SN2. Okay? What? All right. I'm just saying that you didn't see the data, but I have, and I know it's SN2. Okay. Yeah, so that's the answer in this case. Now, with experience, you will come to know that the SN2 reaction depends on the identity of the electrophile and the identity of the nucleophile. And you'll learn how to reason your way to determine what should happen here. We're not there yet, but that's what we're talking about in chapter 7. In contrast, for the SN1 reaction, you'll learn that it's really the alkyl halide that does the determination. Though, in some ways, we'll be able to tell when the SN1 happens by considering what the nucleophile is versus isn't. We will see that, in general, good nucleophiles favor SN2. We will see that poor nucleophiles often have to wait around for the leaving group to leave. And so we will say poor nucleophiles, it's not really accurate to say they favor SN2. Poor nucleophiles have to wait for the leaving group to leave. We're also going to talk about how the structure of the alkyl halide determines the relative rates of SN2 and SN1. If you look at the fact that SN1 has to involve backside attack, then you could imagine some things might slow down backside attack. And one of the major things that can slow down backside attack is sterics. So you will see, for example, that the rate of SN2 is fast for methyl leaving groups and for primary leaving groups. It is slower for secondary leaving groups, and it is too slow to observe for tertiary leaving groups. That is, if the leaving group is attached to a carbon that's attached to 3 other things. And the reason for that is, if you think about backside attack in the leaving group, for methyl and primary alkyl halides, primary leaving groups, and in chapter 17 we're going to be dealing mostly with halides, the pathway for the nucleophile to attack the carbon is relatively clear. For secondary alkyl halides, the path to attack the carbon is more hindered, more sterically hindered. You have more carbon-hydrogen bonds on the backside that are going to get in the way, take up space, and get in the way of the nucleophile. And by the time you get to a tertiary alkyl halide, these adjacent CH bonds totally block the approach of the nucleophile. So we will see that steric hindrance slows the rate of SN2. So one of the reasons I said that I could tell that this reaction mechanism would be SN2 is, first, I looked at the electrophile, and I know that SN2 is generally fast for methyl leaving groups. And then I looked at the nucleophile, and based on some things we will talk about, I identified this as a good nucleophile. So essentially, this is a situation where there's nothing to prevent SN2 from happening. The nucleophile is very reactive. It's not going to sit around and wait for the leaving group to leave. And the electrophile is not sterically hindered at all, so the path is open. So these are some of the things that we're going to consider. All right. Other questions? Yeah.
So with these, basically, when we're going to be determining which one is the backside, front side, the more functional groups are bigger the molecules that are that would interfere with the backside, it's the more it's going to be majority of this one.
Right. The more groups you have blocking backside attack, the more SN1 is going to be preferred. Yeah.
And that doesn't count hydrogen, right?
That doesn't count hydrogen, right? Hydrogen's pretty small.
Okay, so you can say.
Yep. Go ahead.
Is that just because of electron density?
Yep. It's just electron-electron repulsion. Yep. What else? Yeah.
Sorry, going back to that right there. So when your nucleophile attacks, how does it make the dash become a wedge with that repulsion?
How does it make the dash become a wedge with the repulsion? There's two ways to view this. We're viewing the attack from the side here, but you can also view it sort of from above. Part of this is just going to be moving the molecule around in your head, and maybe building a model will help on this. First, I need to convince you that this view of the molecule is exactly the same as this. We're just viewing it from a different perspective. Okay? And second, that this view of this product is exactly the same as this. We're just viewing it from a different perspective. But the point is that the nucleophile comes in from the opposite side as the leaving group. That causes the carbon, the other bonds at that stereocenter to pop the other direction. And then the consequence of that is what I've shown here. Basically, from our perspective from here, the nucleophile is coming up, coming from below and beneath. It's causing this group to leave, and at the same time, it's pushing this hydrogen up out of the page. Yeah?
Would we have to know like A values?
Do you need to know A values to do this kind of reasoning for steric hindrance? No, as long as you understand that a tertiary carbon is going to be more hindered than a secondary carbon, which is more hindered than a primary carbon. Yeah? Right, so SN1 and SN2, there's two words that were asked that I didn't talk about. The SN1 reaction mechanism is stepwise because the bond breaking and the forming happen in different steps. The SN2 reaction is concerted because the bond breaking and forming happen in the same step. All right, one more thing I want to sort of blow your minds with in the last couple minutes, and that is, let's see, sketch, there we go. That is, if you look at this molecule, this is a secondary alkyl bromide. The bromine is the dark red atom, and that carbon-bromine bond is weaker. If I had asked you what the LUMO of that molecule was, you would have told me it was the carbon-bromine sigma star. And you would have expected a node to be here in between the two atoms with a large lobe pointing up and another large lobe pointing down away from the space between the two atoms. This is the LUMO, and you can see it mostly looks like you would expect, except some of it is on the adjacent hydrogens. What on earth is going on there? That's important because starting in chapter 8, which we're not going to get to before the exam, but starting in chapter 8, we're going to see that a nucleophile has the choice to whether attack the LUMO at the carbon or at the adjacent hydrogens. And you're going to need to understand why some of the LUMO is on the adjacent hydrogen. So I'm going to talk about that briefly next time just so that you can expect it. And then we're going to spend the rest of the time before the exam talking about SN2 and SN1. All right, see you then.